Hello, this is Gurumurthy Ramachandran, and today we'll be discussing how to navigate through this Excel spreadsheet called IHMod version 2.0, which is an exposure modeling spreadsheet. So when you get the spreadsheet and you click on it, you will first come up to a screen where you have to click on this accept the terms of a disclaimer, um, and you can click that, and then you come to this screen where you have an option of where it gives you some basic information about the software, the mathematical models for estimating occupational exposure to chemicals, a guide to the different models that are in the software published by AIHA, and in the top right corner you will see deterministic and Monte Carlo models. So this software provides you with both options. So we'll click on the Start button, and now you'll see a whole array of models, starting from the well-mixed box room model to well-mixed room model with back pressure, the purging equation, and so on, all the way down to the near and midfield plume models. For this unit though, I'm just going to demonstrate the use of this with the well-mixed room box model and maybe the two-zone model with constant emission. Now when you come to the right hand side, you will see that there are two sets of arrows. The first set of arrows is for a deterministic model, for the deterministic version of each of these models, and the second set on the right hand side is the Monte Carlo version of each of these models. And let's just click on the well-mixed room model, the deterministic option first. So here, when we say deterministic, we just mean that we can provide fixed values of inputs to each of the model parameters, and the model will predict one set of outputs. And so for the well-mixed room model with a constant emission rate, we see on the right hand side here the various model parameters. G is the contaminant mass emission rate, Q is the room supply and exhaust airflow rate, V is the volume of the room, C0 is the contaminant concentration at time t equal to 0, Cn is the contaminant concentration in the supply air, and case of L is the fraction per minute loss by various mechanisms. And then the seconds in these boxes are where you input the values of the parameters you want. So let's just say we put a mass emission rate, it's already the air of 100, a room supply airflow rate of 100 cubic meters per minute, and the room volume is 500 cubic meters. Let's assume that the contaminant concentration at T equal to 0 is 0. The concentration of the contaminant in the supply air is 0, and there are no loss mechanisms. They're all set to 0%. And so for that set of values, now we come to the graph here, and this is the concentration versus time. So on the x-axis we have time, and it goes all the way up to 350 minutes, and that's because I have set here the maximum time of simulation up to 300 minutes. And you see this blue curve, it starts from 0 and goes all the way up to 300 minutes. We're also saying that the time at the end of the contaminant generation is 250 minutes, which means that the contaminant generation starts at t equal to 0 and goes all the way up to t equal to 250 minutes, at which point the value of the generation rate g becomes 0. So what we see here is that there is a substantial airflow rate, 100 cubic meters per minute, and so the room reaches a steady state concentration fairly rapidly in about 33 minutes or so. And we can also find out the value of the concentration at different points in time. So we can, so if I change this value of the t in this box here, we see two things. One is this ball here moving along, which is the c at t, and so that's, if you look at the CT box here, that's 0.999 or almost 1 milligram per cubic meter, and we can see it's reaching steady state. We can also go down and you can see at very low values at t equal to 3 minutes, the value of the concentration is 0.451 milligrams per cubic meter. And so we can see that the concentration rises rapidly and reaches its steady state value around 33 or 34 minutes, and then it stays constant at 1 milligram per cubic meter all the way up to 250 minutes. And at that point, the concentration starts falling because the generation rate now goes to 0. So from 250 minutes all the way up to 300 minutes, we see the purging of the room of its contaminant in the air. And so there's a rapid exponential decay of the concentration in the room all the way down to 0. So this is the well mixed room model with a constant emission rate. We can play around with various other parameters. For example, if the mass emission rate suddenly doubled, we can see now that the steady state concentration has also doubled. Previously it was 1 milligram per cubic meter, now it's 2 milligrams per cubic meter. We can also study the effect of different loss mechanisms. You can see that when there is 5 or let me just make it 1% loss, so you can see that the steady state concentration is much lower, but also the steady state itself is slowly declining because of the loss mechanisms. And so this is a demonstration of the well mixed room with constant emission rate. We can go back to the first page, come back to the to this array of models, and let's pick a different model now, the two-zone constant emission deterministic model. And in this case, so that's the two-zone model, constant emission rate. So here, again, we have the input parameters for this model. The generation rate G, Q is the ventilation rate, S is the random air velocity, and we are selecting a hemispherical near field shape, and the room volume is given to be 42 cubic meters. The near field volume is 1.77, and the far field is 4.23. When we select a near field shape, which is a full sphere, or we can also choose half of a sphere, then the radius of this sphere is something we need to input. So we are inputting a value of 0.75 meters, and which means that we can automatically calculate the surface area of the hemisphere, and thereby the value of beta, which is the airflow through the free surface into and outside of the out of the near field. And so that's how the free surface area and beta values are calculated. We can set the time for simulation, and so I'm going to set it to 350 minutes as before, or let's make it 300 minutes. And the time at the end of generation, let's make it 200 minutes. And just as in the previous case of the well mixed room model, we can find the value of the concentration at different points in time. So here right now the cursor is at 75 minutes, but we can change that value to whatever we want, and we can read the exact value. So here the cursor is at 30 minutes, and we can find the value of the near field concentration and the far field concentration at t equal to 30 minutes. So that's about almost 19.4 milligrams per cubic meter for the far field, and 76.2 milligrams per cubic meter for the near field, and they are also shown in these boxes, or you can observe them visually. You can also see that the equations are predicting that both the near and far field concentration profiles, they have a period of rapid increase, and then they reach some steady state. And so the steady state for the near field is shown in blue, the steady state for the far field is shown in red. And the steady state is maintained till the point where we have said at t equal to 200 minutes the generation stops. And so at that point both the concentrations decrease rapidly in an exponential fashion and go down to close to zero rapidly. So this is the two-zone model with constant emission. One other feature of this software is that you can click on this TWA concentration button, and the dotted lines provide you with the time-weighted average concentration as a function of time. So the way to interpret this is that, let's say at t equal to 100 minutes, we want to know what the near field time-weighted average concentration is. That is roughly 74.5 milligrams per cubic meter. So what it means is that if you were to take an average of the entire concentration profile from t equal to 0 to t equal to 100 minutes, then the average concentration is around 74.5 milligrams per cubic meter. Similarly, the average concentration from t equal to 0 to t equal to 100 in the near field is roughly 18.2 milligrams per cubic meter. Okay, now let's go back to the home page and click on the start button. But now we will look at the Monte Carlo option. So here, for the sake of simplicity, I'm just going to show the well mixed room model again. And so unlike in the case for the deterministic model, where we supply one value of G, 100 milligrams per minute, for example. Here you actually supply a distribution for the values of G and the values of Q. So we have several possible distributions from which to choose. We can always choose a fixed value, in which case we revert to a deterministic model, but we can choose a normal distribution, a uniform distribution, a log normal, or a triangular distribution. So let's just pick a normal distribution for G, and the normal distribution has the parameters as shown here. So it has an average value of 50 milligrams per minute and a standard deviation of 6 milligrams per minute. Likewise, the ventilation rate Q can also be described by a distribution, and the same distributions are available for this parameter also. And so let's assume that the Q is described by a uniform distribution with a minimum of 36 and a maximum of 540 cubic meters per minute. And the other parameters are set as follows. The room volume is 200. The contaminant concentration at T equal to 0 is 0. Contaminant concentration in the supply air is 0. There are no loss mechanisms. The maximum time for simulation, let's just again set it to be 300 minutes, and the time at the end of generation, let's say that's 250 minutes. And now I start my simulation, and then I click this button, and we see this form of a distribution where the contaminant concentration rises, and then it reaches a steady state all the way up to T equal to 250, and then it decreases. Okay, let's re-record from the point where I'm starting to describe the simulations here. So I'm going to set the generation rate G to be a normal distribution with an average or mean of 50 and a standard deviation of 6 milligrams per minute. The ventilation rate Q can be described by a uniform distribution with a minimum of 36 and a maximum of 540 cubic meters per minute. The room volume is 200, and then the maximum time for simulation is 30 minutes, and the time at the end of generation is 25 minutes. And I'm going to do 10,000 iterations of this model. And now when I see my output, you can see several different, and now when you see the output, you see several different outputs shown in this. So the dark solid black line that's bolder than the other ones, that is the median value of the 10,000 simulations. And so you can see it rises up, reaches a steady state value, and at time 25 minutes it starts an exponential decay back down to 0. But the plot also shows the several other percentiles. So the median is the 50th percentile, but the output also shows the 75th percentile plot, the 95th percentile plot, as well as the 25th and the 5th percentile plots. So what this output is showing is the range of outputs that the range. What this output is showing is the range of values that the concentration in the room can take, depending on the particular value of G and Q. And so while the median output is probably most likely, the range of outputs that are possible range from the 95th to the 5th percentiles. Let me repeat that again. So what this plot is showing is not only the median output, which is the middle value of the range of outputs that we can expect, but also the 95th percentile of the outputs, as well as the 5th percentile of the outputs. So the way to interpret such a graph is that for the range of values for that the generation rate and the ventilation rate can take, we can expect a range of output values ranging from somewhere around the 5th percentile to the 95th percentile. So this is the uncertainty. At every point in time, we can say from the 5th to the 95th percentile, this is the range of values that the concentration output could be located in.